Bonjour everyone, and welcome back to Once Upon a Lecture. I'm Belle, and I'm going to be sharing with you a tale as old as time. We're going to be talking about the normal distribution and z-scores. You may remember that in our last lecture, we learned about standard deviation and standard scores. This is an extension of that lecture, so if you haven't watched that one, you probably should watch that one first, and then come back and join me to learn more about the normal distribution and z-scores. Here's an overview of what we'll be talking about today. We're going to start by talking about the normal curve and particular elements that are unique to the normal curve and the normal distribution. Then we're going to learn about a special normal curve table that we're going to use to help us calculate various percentages of scores that fall within the normal distribution. And we're going to wrap up our discussion by talking about the area of a z-score. This will all make much more sense once we get started. So please be my guest. So let's start talking about the normal curve. The normal distribution or normal curve allows us to attach probabilities to events or scores, and vice versa, to attach different scores to different probabilities. When we talk about probabilities, we talk about the likelihood for particular scores to occur. We plot these probabilities on a normal distribution. So when we plot the normal distribution, typically the x-axis, the horizontal one, represents some type of score, and the y-axis represents the probability of that score occurring. So essentially you have score and probability plotted on the two axes. Contrary to common belief, most data that we encounter are not normally distributed. But if we increase the number of sample means we obtain from a larger population, the more normal the distribution becomes. In other words, we know that it is virtually impossible for us to collect data from entire amounts of large populations. So what we do is we take samples from these larger populations and evaluate data points relative to those samples. When we evaluate data from those samples, the data typically do not match the normal curve. In other words, we do have skewness, we do not always have symmetry, and the mean, median, and mode are not always going to be the same number, which are qualities that do pertain to a normal distribution, but do not pertain to what we call a sampling distribution. A sampling distribution is a distribution of the data that we typically collect. A normal distribution is this ideal, perfect, normally bell-shaped curve to which we compare our sampling distribution. Therefore, if a population is large, we typically want to take more than one sample from a given population. If we continue to take sample after sample after sample, the idea and the hope is that at some point our sampling distribution will match the normal distribution. In other words, the scores will normalize, will balance out, and will be symmetrical. So if we relate data points to a normal curve, we know that 100% of the scores will fall underneath it. We also know that 50% of the data points of a normal curve fall to the left or below the mean, and conversely, the other 50% will fall to the right or above the mean. Only 13.59% fall within 2 standard deviations above or below the mean. Only 2.15% fall within 3 standard deviations above or below the mean, which means that the majority of scores are concentrated around the mean within 1 positive and 1 negative standard deviation of the mean. So a standard normal curve is special because it is symmetrical. It has one mode, meaning it's unimodal, and the mean, median, and mode are all the same number. In a standard normal curve, we also know that the mean is equal to 0 in standard deviation units, and each standard deviation is equal to 1. Given this information, we can actually find the percentages of scores that correspond to various standard scores or z-scores. And in order to be able to do that, we have to learn how to use the normal curve table. So let's take a look at what that is. Typically, the data we collect are represented in a raw score format. To better understand how certain scores fall in a normal distribution, we convert them from raw scores to standard scores using the z-score formula. This is what the z-score formula looks like. Z is equal to the score, represented by X, minus the mean of our distribution, divided by the standard deviation. Similarly, we can find a raw score that corresponds to a given z-score using the raw score formula. So in this case, X is the raw score that we are trying to solve for, and X is equal to Z, the standard score, multiplied by standard deviation plus the mean. Remember, order of operations are very important when it comes to formulas, and multiplication supersedes addition. So make sure that you know you have to multiply the z-score times the standard deviation first, and then that product is going to be added to the mean. So after converting raw scores to z-scores, we can then identify the probability of the total distribution that received that particular score. And we do this using the normal curve table. So this is a portion, a small part of the normal curve table. The table typically ranges from a z-score of 0 to 4, since most of the data points fall within 3 standard deviations above or below the mean. 4 is kind of our maximum cutoff point. You may think to yourself, well, why wouldn't we cut it off at 3? Well, the answer is because sometimes we do have 0.0001% of the population that will score some particularly deviant score above or below the mean. So we do need to exceed the standard deviation of 3, but we cannot exceed the standard deviation of 4. So again, this is just to say that the normal curve table directly corresponds with the standard deviation units seen on a normal curve. So if you think back to the bell-shaped curve and the x-axis, you will remember that we have the mean in the middle with a standard score of 0. Then you have +1 and -1 standard deviations above and below the mean. Then you have +2 and -2 standard deviations above and below the mean. And then you have +3 and -3 standard deviations above and below the mean. Oh, that was a tongue twister. So the table is going to represent those same standard deviations. However, given the fact that z-scores can be positive or negative, it's important to remember that the chart will only show you positive values. But if you are looking up a z-score that is 3 standard deviations below the mean, it is our responsibility as researchers to give it a negative sign so that when we do plug it into the formula for calculations, we are in fact considering the negative z-score and not the positive one. So a negative z-score is indicated if it is below the mean, and a positive z-score is indicated if it is above the mean. So we use the same chart for both positive and negative z-scores. The difference lies in which column we're going to use for our calculations. I know that sounds a little foreign right now. You're thinking, what calculations, what column? So if you look at this chart a little more closely, you can see that there are 3 different columns relative to each z-score. The A column represents the various z-scores we can obtain when converting raw scores into z-scores. So we call this column A, and you can also see that it has a heading of a lowercase z. That means that this is the column in which all of the z-scores are listed. The B column represents the percentage of the area of the population that falls between the mean and the z-score. For example, if z is equal to -2 and the mean is 0, the distance between -2 and 0 will be shaded. That is the area, the percentage that we are going to be identifying. And the B column gives us that percentage. The C column represents the percentage of the area that falls farther from the z-score. So in other words, it's going the opposite direction of the mean, because the distance between the z-score and the mean is given to us by the B column. The C column is going, you can think of the C column as being away from the mean. And so here's a visual representation of what that might look like. You can see that the mean is set at 0. We can see -1 is the z-score we have. And so the C column is going to show us the direction to the left of -1, to the left of our z-score. So understanding how these columns work is really important in order for you to be able to calculate the percentage that lives within the area under the normal curve. So let's talk about some specific examples related to finding the area of a z-score utilizing the normal curve table. The first thing we need to do is draw a normal curve. I guarantee you that majority of the mistakes that we make are not due to calculation error, but simply because we don't understand the concept of what the question is asking us. I highly recommend drawing normal curve tables for each question so that you're able to visualize the relationship between the mean and the z-score and the area that you're going to be shading, the percentage that you're going to be finding for each question. So definitely get used to drawing a normal curve. After you've drawn the normal curve, you always want to label the axis with a standard deviation of 1 and setting the mean to 0. After that, you're ready to convert the raw scores into z-scores. Once you have the z-score, you're going to use that z-score, go to the normal curve table, and identify the area that corresponds with that z-score. And this, as I mentioned, is the most important part. It is also the trickiest part because it really depends on looking in the proper column. So we're going to spend more time understanding the concept of the question being asked of us as opposed to spending more time on how to calculate it. So let's take a look. The beast has found that the average height of the 1,250 inhabitants in his kingdom is 71 inches. With a standard deviation of 2.3 inches. Using the normal curve table, we need to answer the following questions. How many people are at least 75 inches tall? How many people are between 65 and 72 inches tall? If a townsperson is at the 35th percentile in terms of height, how tall is she or he? Assuming the tallest top 10% of the people receive higher salaries, how tall does one have to be to get a better salary? What is the probability of encountering someone who is 66 inches tall or less? And lastly, what heights are so deviant that their probability of occurrence is 0.05 or less? So I know that this is a lot of questions, but each question is kind of unique in its own way. So I want to make sure that we go through a variety of different question types related to the normal curve together so that should you encounter one of these questions in your own research, you will know exactly what to do. So let's start with the first one. How many people are at least 75 inches tall? The first thing we need to do is draw a normal curve table and label that x-axis. So again, 0 is our average. We move in units of 1 for the standard deviation. Our minimum is -3 and our maximum is +3. Done. The next thing we need to do is convert the raw score of 75 into a z-score. Remember, the question about how many people are at least 75 inches tall means that 75 inches is a raw score. What we need to do is convert it. We also know that the mean height, the average, is 71 inches, and the standard deviation is 2.3 inches. And the total number of people in the kingdom that we're surveying is 1,250. So these are the data points that we need to know because they are relative to our formula. Z is what we're trying to calculate. It is equal to X, which in this case is 75, minus the mean, which in this case is 71, and we divide by the standard deviation, which is 2.3. If we do 75 minus 71 divided by 2.3, we get a z-score of 1.74. 1.74 is a positive z-score. That means this is almost 2 standard deviations above the mean. So now we need to place that z-score onto the normal distribution. Remember, the z-score of 1.74 corresponds to a raw score of 75. This is the same as saying 1.74 standard deviations above the mean. So again, the score is positive, which means we will plot it above to the right of the mean. If the mean is 0 and our z-score is 1.74, that's a little bit closer to the 2 than it is to the 1. So this is where it would appear on a normal distribution. Now, using the normal curve table, we need to find the percentage area that corresponds to a z-score of 1.74. Remember, the question was, how many people were at least 75 inches tall. So that could refer to people who are 75, 76, 77, etc. It refers to people who are 75 inches tall and taller, but it does not refer to people 75 inches or shorter. So we know that our z-score is 1.74. In this table, let's go ahead and in the z column, locate 1.74. Once you've located it, you should put your finger on it. And then we need to determine if we have to look in the B or the C column to answer our original question. If we think about it, we know that at least 75 means at a given score and taller. So we're going to shade in the area to the right of the z-score. So in other words, this is going opposite the mean. This is not the distance between the z-score and the mean, because that would indicate people who are shorter than 75 inches. We're looking for 75 inches and taller, so we're going to shade the area to the right. This is also a good indication that we should be looking in the C column. The C column is the area beyond Z. Because we're looking to the right of Z, the opposite of the mean, that is the column we need to be looking in. And we can see that that number is actually 4.09 or 4.09% essentially is what this means. So the area that is shaded in our normal distribution right now, that is shaded in pink, represents 4.09 percent of our distribution. So 4.09% of our data set is taller than 75 inches. However, the question was, how many people are 75 inches tall? The question was not what percent, the question was how many. So ultimately what we need to do is calculate 4.09% of 1250. There are two ways to do this. You can either take your calculator and multiply 4.09 and use the percent symbol and multiply by 1250, you will get 51.125. And it's totally recommended to go ahead and round to the hundredths place. So you could say 51.13. Make sure you are using the percent symbol on your calculator. If you do not have a percent symbol, that is totally fine. You can go ahead and convert 4.09% into a decimal simply by moving the decimal place to the left 2 times. So if we do that, we get 0.0409 multiplied by 1250, and you get the same result, 51.125. So to answer our original question, approximately 51 people are at least 75 inches tall. You notice that 51 has a decimal after it, but we can't really say that 51 and a half people. So what we're going to do is we're going to round to the nearest whole number, which in this case is 51. So how many people are at least 75 inches tall? Approximately 51 people. Question number 2. How many people are between 65 and 72 inches tall? Again, the first thing we need to do is draw the normal curve and label that axis. The mean and the standard deviation and our n do not change for any of our questions because we're still dealing with the same data set. So again, 65 and 72 are both raw scores. We need to convert those into z-scores, but now we have 2 different scores, so basically we do it 2 times. Let's start with 65. If we place 65 in place of x, we're going to have 65 minus 71 divided by 2.3. That's going to give us a negative z-score of negative 2.61. That means this is 2.5 standard deviations below the mean. Then for a raw score of 72, we do the same thing. We substitute 72 in place of x. 72 minus 71 divided by 2.3 gives us a positive z-score of 0.43. So now we need to place the z-scores on the normal distribution. Our z-score for 65 is negative 2.61, which is on the far left. And our z-score for 72 is positive 0.43, which we can see slightly to the right of the mean. So we can see that we will need to find the area between the z-score of 0.43 and the mean. And we can also see that we will need to find the area between the z-score of 2.61 and the mean. So because we need to find the area between the z-score and the mean, this indicates to us that we're going to be looking in the B column of the normal curve table. So once again, we come back to the normal curve table and we need to find the percentages that correspond with the z-scores we've calculated. First, let's go ahead and find 2.61 in the z column, and then we need to slide our finger over to the B column to find the percentage that corresponds to the area between the score and the mean. Remember, the C column tells us the area beyond Z, away from the mean. But in our case, the area that we are interested in is actually between the mean and the Z-score. Then we're going to do the same thing for the Z-score of 0.43. Place your finger on 0.43 in the Z column, and then look in the B column relative to that Z-score to see what area corresponds to a Z-score of 0.43. And we can see that that is 16.64%. So now our distribution would look something like this. The area for Z-score of 0.43 is shaded in green. The area for Z-score of 2.61 is shaded in blue. Our goal is to find the area of the total shaded section. So what we need to do is add up the percentage of the blue with the percentage of the green, because that's going to give us the total area under that curve. So if we add 49.55% plus 16.64%, we get 66.19%. So in other words, this entire shaded area, the blue shade plus the green shade, represents the combined percentage for both z-scores together. So again, going back to our question, how many people are between 65 and 72 inches tall? The fact that we're asked how many people means we need to report a whole number instead of a percent. So going back to the same thing we did before, we need to find what is 66.19% of 1,250. Again, remember to use your percent symbol or convert your percentage into a decimal number. Doesn't matter which one you choose, you should end up with the result of 827.35. So approximately 827 people are between 65 and 72 inches tall. Moving on to question number 3. If someone is at the 35th percentile in terms of height, how tall are they? So again, the first thing we do is draw a normal curve and label the axis. We know the same given information about the mean and standard deviation, but in this case, instead of calculating the z-score, we need to calculate the raw score using the formula x equals zs plus the mean. Why? Because we need to find the z-score that corresponds to a percentage of 35. The word percentile represents everything at a given score and below. Because we know that every z-score corresponds to a particular percentage under the curve, we can reverse the process, and if we have the percentage, we can then locate the z-score that corresponds to it. Once we find that, we can plug it into the raw score formula to understand which raw score height is going to be at the 35th percentile. Remember, percentile means everything at a given score or below. So we need to identify which z-score corresponds to a percentage of 35%. Remember, the question asks about percentile. Percentile means at a given score or below. So is 35% higher or lower than our mean, or our median, I should say, which is 50%? 35% is less than 50%, so we know that it's going to fall somewhere on the left side of the mean. Now, because percentile means at a given score and below, we know that we're going to be looking at the area beyond z. We are not looking at the area between the z-score and the mean, we're looking at the area opposite. So this suggests that we will be looking in the C column, since we're looking at the area to the left of the mean. We're looking at everyone who is in the 35th percentile, who is that height, which we don't know yet because we need to solve for x, but who is a particular height at the 35th percentile and shorter. So by looking in the C column, we can we're going to try to find the number closest to 35%. You will notice that sometimes the percentage, the exact percentage you're trying to find, doesn't exist in the normal curve table. There may be decimals that will bring you close to your desired value. So our desired value to locate is 35%. We can see the score that most closely resembles 35% is 34.83. If you slide your finger to the left to see the z-score that corresponds with this percentage, you will see that the z-score is 0.39. But remember, because we're talking about a value that is below the mean, it's very important that you indicate that this z-score is negative. So this is the z-score, negative 0.39, that we're going to plug into our raw score formula in order to figure out which score is at the 35th percentile. So once we do that, we have the fact that x is equal to the z-score multiplied by standard deviation plus the mean. So now if we substitute the values in the formula, we have x is equal to negative 0.39 multiplied by 2.3 plus 71. So once we solve for the formula, we can see that the raw score that corresponds to the 35th percentile of our distribution is 70.103 inches, or 70.10 inches. All right, moving on to question number 4. Which height is at the top 10% of the distribution? Again, in this case, instead of calculating the z-score, we need to calculate the raw score using the formula x equals zs plus x. Why are we using the raw score formula? Because we can only use the z-score formula if we know what the raw score is. But in this case, we are given the percentage value underneath the normal curve. We can use that percentage to identify the z-score that corresponds to it, and using that z-score, we're able to identify the raw score that represents the height at the top 10% of the distribution. So if we need to find the z-score that corresponds with this area, it's going to be around this vicinity here. We know if we're talking about top 10%, it means 10% and higher. So we need to find the z-score that corresponds with an area of 10%. And because we're talking about top 10%, this is again going to tell us that we're looking for the area to the right of the z-score, the top 10%. So if we move to the left of the place where we have it marked on our normal distribution, that's going to show us the scores below the top 10%. We're interested in the top 10%, so we're going to be looking at the area to the right of this percentage mark. So again, if we have the percentage, we need to find the z-score that corresponds with that percentage. So the top 10% indicates that the z-score will be above the mean, because remember, the normal distribution is split, the 100% is split in half. The middle point is 50%. Everything above 50% is going to be on the right side. Everything below 50% is going to be on the left side. If it's the top 10%, it means this is the top of the distribution, the highest end. So we're going to be looking at the right side of the distribution. Because this is the area that we're interested in, we're going to be looking in the C column. The C column is the area beyond Z. Remember, the B column would tell us the area from the z-score to the mean, which is not what we're interested in. Top 10% is indicating that we want to look higher, above. So if we look in the C column and we find the value that is closest to 10%, or the number 10. Looking in this column, we can identify that the closest value to 10% is 10.03. If you slide your finger to the left of that, you will see that the z-score that corresponds to this percentage is 1.28. So you ask yourself, is this going to be a positive z-score or a negative z-score? Well, it's all about its relation to the mean. Is this data point above the mean or below the mean? If it's above the mean, it's going to be positive. If it's below the mean, it's going to be negative. In this diagram, we can see that it's definitely above the mean. Top 10% is definitely above the mean, so the z-score will be positive. Now you're going to plug that z-score into your formula. So x is equal to 1.28, which is our z, multiplied by a standard deviation of 2.3, plus the mean gives us a score of 73.94. So to answer our original question, the height in the top 10% of the distribution is 73.94 inches. Question number 5. What is the probability of meeting someone 66 inches tall or less? The key phrase "or less" indicates to us that we're going to be looking at the raw score of 66 and everything below that. So once again, given the data that we have, let's go ahead and draw our normal curve. The next thing we need to do is convert the raw score of 66 into a z-score. Notice the question is no longer giving us a percentage under the curve. The question is no longer giving us a z-score. The question is telling us a raw score, a raw height of 66 inches, and asking us to identify the probability. So essentially what we need to do is convert the raw score of 66 into a z-score. So you should know the formula by now. Z is equal to the score minus the mean divided by standard deviation. My score is 66 in this case. My mean stayed 71 and my standard deviation stayed 2.3. When I divide those, I get a z-score of negative 2.17. The z-score is negative because it is below the mean. So a z-score of negative 2.17 would fall somewhere along here on our normal curve. So going back to our normal curve table, we now need to find the percentage area that corresponds with the z-score of negative 2.17. Remember, the chart only gives you positive numbers, so if you know your z-score is negative, that's okay. It's symmetrical. Whatever values you see here for positive z-scores would be the same for the negative side of the distribution. So let's go ahead and find 2.17 in the z column on the chart. So if we are looking for the percentage related to the z-score of 2.17 or less, a height of 66 or less, that means that we're going to be looking in the C column to find the area to the left of the z-score. We are looking for the percentage that corresponds beyond z. So if my z-score is 2.17 and I'm looking at the area beyond z, I'm going to be looking in the C column. I can see that that value is going to be 1.50 or 1.5%, 1.50%. So that is the area that corresponds to a z-score of 2.17. It is also the same percentage that's going to correspond to a negative z-score of 2.17. So going back to our original question, what is the probability of meeting someone 66 inches tall or less? Now that we've found the area corresponding to a raw score of 66 and a z-score of negative 2.17, we have to divide the percentage by 100 to obtain the probability. The formula for calculating probability of a score is dividing the percentage of the area by 100. The percentage for our area in this case is 1.50. So if we divide 1.50 by 100, we get a probability of 0.015. So a score of 66 has a 0.015 probability of occurring. In other words, the probability of meeting someone 66 inches tall or less is 0.015. As you can see, and as we'll learn later in another lecture, the maximum probability something can occur is 100% or 1 whole. So given that this number is very far from the number 1 or 100%, so the probability is very small for you to meet someone shorter than 66 inches within the beast's kingdom. Question number 5. What heights are so deviant that their probability of occurrence is 0.05 or less? If we convert the decimal 0.05 into a percentage, we know that that is going to be 5%. So essentially the question is, which scores are so rare, are so deviant that they're going to happen less than 5% of the time? Notice that this question does not specify if the scores are deviantly high or deviant on the low end. So we have to consider both sides of the extremes, meaning both positive and negative. So while the question states the probability is 5%, because we need to consider both the higher and the lower end, we need to split 5% into 2. So if we divide 5% by 2, we get 2.5%. So you're going to look for the probability of a score that occurs 2.5% above the mean. And we're also going to look for the probability of a score that occurs 2.5% below the mean. So in this case, because we are given percentage instead of a raw score, we know that we're going to use the normal curve table to find the z-score that's associated with 2.5%. Another way of saying 2.5% is 0.025. So looking at this chart, because we know that the area we are interested in is away from the mean, is the area beyond z, we know that we're going to be looking in the C column. So what we need to do is find the closest value to 2.50% in the C column. Once we do that, we can see that the z-score that corresponds to 2.5% is 1.96. Remember, 1.96 is relative to the positive end, but we use the same z-score, 1.96, to represent the negative end of our distribution. So we have a positive z-score of 1.96 to represent the 2.5% probability of a score deviantly high. And then we have a z-score of negative 1.96 to represent the deviantly low scores on our distribution. So now that we know which z-score corresponds to the top and bottom 2.5% of the distribution, we plug them into the raw score formula. So our raw score formula says x equal to zs plus the mean. The first one we'll do is we'll take the positive z-score, and we have 1.96 multiplied by 2.3 plus 71 gives us a raw score of 75.51. The second z-score we plug in is negative 1.96 multiplied by 2.3 plus 71 gives us 66.49. So to answer our question, the lowest deviant height is 66.49 inches and the highest deviant height is 75.51 inches. Whew. I know that was an incredibly long lecture. I know that was a lot of information to take in, but the good news is that you can replay it as many times as you want. Hopefully this lecture was helpful in helping you better understand the normal distribution, the normal curve, how to use the normal curve table to find percentages under the normal curve, and additionally helped you understand how you can find the raw score if you already know the z-score or the percentage of the distribution that achieved a particular score. So if you feel like you need a reminder or a refresher to remember how to calculate standard deviation and see how standard deviation refers to standard scores and z-scores on the normal distribution, definitely check out Dorothy's tutorial video on measures of dispersion. I hope that you enjoyed this lecture, and I look forward to seeing you again here on Once Upon a Lecture.